Welcome! After having looked at the main components of geothermal systems, we want now to devote our attention to how geothermal fields are discovered and how they are exploited. Eventually, we will mention some of the technical challenges facing geothermal energy. With increasing need for clean energy and with technological progress, the spectrum of settings and places suitable for geothermal energy has substantially expanded. Systems characterized by very deep aquifers and/or by low temperatures, which were considered as useless until a few years ago, are now fairly attractive. Now, letting aside the simple and very shallow borehole heat exchangers, we make a distinction between low-temperature systems, where heat is extracted from the aquifers, and high-temperature systems, where very hot water and/or steam are used to produce electricity. As a result, geothermal energy has now a very wide range of applications. High-temperature geothermal systems are characterized by having very high temperatures, typically with gradients of more than 100 degrees per kilometer. Such abnormal values are always associated with magmatic intrusion and result in strong convective movements of water which reaches the surface in natural fashion, producing fumaroles and high-temperature springs. Waters are strongly contaminated by the degassing of the intrusion, resulting in widespread precipitation of various minerals and smell. Because of their apparent characteristics, most of the areas of potential geothermal interest have already long been known, and the challenges have more to do with the exploitation than with the exploration and discovery. Standard geophysical tools such as seismic, electromagnetics, and gravity are used to define the architecture of the field, inclusive of the definition of the reservoir, the seal, and very important, the main faults. The exploration boreholes generally follow to better define the geological and the geothermal models, inclusive of the position of the isotherms. A large amount of investigation is then applied to constrain the hydrogeological model, which implies a good knowledge of the path followed by the fluids, of the amounts involved, and the temperature changes they experience. The analysis of geochemical data is also of great help. Structural studies are important to define the permeability of faults and other fractures and are coupled with geochemical tools to constrain the trajectories followed by fluids. The field now is ready to be exploited. Extracting energy from high-temperature fields is relatively easy, as water, sometimes in the form of vapor, rise spontaneously to the surface. At the surface, turbines or other condensing units transform the vapor into electricity, which is then distributed through the standard network. Increasingly common are systems which use a secondary fluid with a lower boiling point to create steam. A major challenge to a high-temperature system is given by the chemically aggressive nature of fluids associated with magmatism, and with the high temperature at which underground operations must take place. All in all, the exploitation of high-temperature fields is relatively straightforward, and the economic challenges relatively limited, mainly because electricity can be easily transported at large distances. The downside is, unfortunately, the high-temperature fields are not that common. Low-temperature geothermal fields, on the contrary, have thermal gradients which are only somewhat higher than normal, are not necessarily associated with magmatism, and are not related to apparent manifestation at the Earth's surface. In fact, all areas with a not too deep aquifer at temperatures above 70 or 80 degrees are potentially interesting for exploitation. In low-temperature geothermal fields, injected cold waters heat up in the aquifer and are then pumped to the surface to produce heat, not electricity. Different from electricity, heat dissipates easily, and the success of a low-temperature geothermal field depends on the amount of hot water which can be extracted and eventually delivered to the users. Correct prediction of the temperature and the hydrogeology of the system, permeability, flow, etc., is therefore absolutely crucial, as small deviations can imply the success or failure of the exploitation. The definition of the overall geometry of the target reservoir is generally relatively easy and is based on standard geophysical tools such as seismics. Typically, is then refined by exploration wells. These wells are also used to a certain temperatures of the aquifer. Possibly the greatest challenge facing the building of the hydrogeological model lies in the definition of the permeability of the aquifer. As we have seen several times in previous clips, this is spatially very heterogeneous at various scales. Especially in systems like fluvial sands, the lateral continuity of the reservoir can be seriously hampered by, for instance, thin layers of shales, very common in these sedimentary systems. Low temperature fields function in a very different way from the high temperatures counterpart. The main difference being the waters need to be injected into the aquifer and then extracted with pumps. For this purpose, all low temperature geofields use injection and producing wells. Obviously, the communication between these wells must be very efficient. In the case where reservoir permeability is the same in all directions, then the relative position of the two wells is not so important. If, on the contrary, a region is affected by systematic fracture sets and or by fault zone, good knowledge of permeability changes is needed. As you can see in this picture, for instance, the flow between wells in A will be much easier than between B and C. Low temperature fields produce heat, which is extracted from hot fluids. All fluids, however, have a strong tendency of cooling and will lose some of their heat during the path from the subsurface to the end users. This poses major limitation to the distance between the energy source and the consumer, typically not more than several kilometers. To be economically viable, a strong public partner must be present in order to facilitate the emplacement of the expensive infrastructure, such as pipes. On the other side, once the system is there, exploitation is cheap. In addition, and especially when targeted the aquifer is deep, the user must have a size large enough to justify the infrastructure investments. Successful examples of consumers are, for instance, hospitals and greenhouses, which need large amounts of energy over the entire year. An interesting case of geothermal energy exploitation is provided by the Netherlands, surely not what we would define as a high thermal grade region. Here, the search and use of geothermal energy is of great importance and, interest enough, was triggered by the agricultural sector, more specifically by greenhouses. Because growth curves of vegetables and fruits are strongly temperature dependent, the greenhouse sector has always used large amounts of energy, typically gas. By extracting water from aquifers of depths of 2 or 3 kilometers, they are able to save significant amount of money, triggering geothermal exploration and development in the Netherlands. Sometimes, things start from a very unexpected source. Like all forms of human activity, and in particular the industrial ones, exploitation of geothermal energy has a number of challenges, which need to be addressed and included in the workflow in order to minimize their impact. The first one is the mechanic and chemical stimulation of the reservoir, also called EGS, which is needed to increase reservoir performance. This technique consists in the injection of high-pressure fluids in the rock, stimulating the formation and growth of fracture at tens of meters around the borehole. Risks associated are the possible reactivation of pre-existing faults. We will look at this in a few slides. The second is the environmental impact. High temperature fields are associated with the emission of potentially polluting gases such as carbon dioxide, hydrogen sulfide and methane. As we have seen, carbon dioxide contributes to global warming. Most of these gases are captured at the point of emission and partly re-injected into the ground. In the case of CO2, this process, which is also widely used in the hydrocarbon industry, is called carbon capture and storage, CCS. Re-injecting gases or other fluids from geothermal plants is obviously something to be done with the greatest care in order to avoid polluting aquifers and posing mechanical threats, as we will see in the next slide. Injecting or extracting fluids from the subsurface has also mechanical consequences, some of which we mentioned already previously. Induced seismicity is probably the most well known. When water is injected, for instance for stimulation, this might reach pre-existing faults. The water under pressure can enter the fault zone, decreasing the stress along the fault and facilitating the slip of the two blocks. This can create an earthquake. Induced seismicity is indeed a recurrent theme in hydrocarbon as well as geothermal fields industry. A detailed knowledge of the subsurface and in particular of the faults and their state of stress is of key importance. On the other side, the scientific community is still far from being able to predict the occurrence of earthquakes. Paradoxically, our incomplete understanding of induced seismicity is documented by the observation that the majority of hydrocarbon geothermal fields are not associated with any above normal seismicity. Despite the challenges and dangers associated with the exploitation of geothermal energy, there is no doubt that it will play a major role in the future in providing part of the energy the world needs. The great advantage of thermal energy is that it is clear and it produces much less carbon emissions than fossil sources. Interestingly, a large part of geological knowledge and expertise you need to develop and exploit geothermal energy is very similar to what developed in the hydrocarbon industry. The two have very much in common. Having a good understanding of geological processes will help you in both. I hope that the GeoMOOC has helped you in reaching these goals.